So now that we've covered various Java synchronizers that appeared in Java 5 and beyond, things like reentrant lock, things like condition object, we're actually going to take a big step backwards to the dawn of Java, Java 1, and its support for built-in monitor objects. And you'll see why that's important, if for no other reason than your next programming assignment requires you to be facile with built-in monitor objects. So it is indeed important to understand how they work. So we'll talk about this. It turns out that built-in monitor objects are really something that's kind of part of the Java programming language. You'll see there's synchronized keyword, for example, that's a keyword that's built into Java, as well as some things that appear in a very fundamental class called the Java object class. Everything in Java extends Java object one way or another. Well, almost everything. There's more recent stuff like Java records that don't extend object, but almost everything else does. So monitor objects are actually part of Java, and they are written in C and implemented in the Java virtual machine, or the Java execution environment. There are two primary types of synchronization mechanisms supported by Java's built-in monitor objects. And the first mechanism, we've talked about this many times before, this is mutual exclusion. And that's the mechanism, of course, that ensures that a thread never enters its critical section at the same time that another concurrent thread is already running in the same critical section. So that's basically what mutual exclusion is about. It's about keeping things out of critical sections. The example that I always give, as you well know by this point, is the restroom protocol on an airplane. And the second mechanism, synchronization mechanism that's supported by Java built-in monitor objects, is coordination. And this ensures that interactions between threads occur in the right order and under the right conditions. And so we'll get a chance to see how that all works. And you might also think in the back of your head, gosh, mutual exclusion, that sounds a lot like reentrant lock. Gosh, coordination, that sounds a lot like condition object. Well, yes, that's correct. Those are classes that were added later in Java to give a more featureful mechanism, set of mechanisms to do mutual exclusion and coordination, whereas built-in monitor objects were the early attempt at doing this, and they're more tightly coupled. They're maybe arguably more efficient, but they're less flexible and more limited too. You can also use Java built-in monitor objects to implement other kinds of synchronization. For example, you can implement various kinds of atomicity properties. You can implement barrier synchronizers. As you will see for assignment 2B, when we get to that point, you can also use them in order to implement other synchronizers altogether, like semaphores, for example, which we will be doing. Any Java object can be used as a monitor object. And there's that, as it talks about here, this I actually have to update this thing. There's now something called a record, and records are essentially not objects, and they're not monitor objects. But so that is actually now true. There's something called records that are not objects, but any Java object that's not a record, it can be used as a monitor object. Methods that require mutual exclusion must either be marked as synchronized, as we do here, or you can use synchronized statements as well. And the key thing, of course, if you use synchronized, is only one thread at a time is able to execute within the call to a synchronized method on a given object. So that's what's used to define the bounds of a critical section using a Java built-in monitor object. And again, keep in mind, as we will discuss further, you can either make the method be synchronized, or you can make blocks or statements within the method be synchronized. And that's the way you do it here. So you can also have methods that are not synchronized methods in terms of their signature, or in terms of what's syntactically shown here. The synchronized keyword is actually not inherited, interestingly enough. But if you have methods that are not synchronized explicitly with the synchronized keyword, you can always make them synchronized internally by using synchronized statements. Now, as we will soon see, synchronized methods and statements are not a complete solution for the kinds of things you want to do with synchronization in Java. There's more to the story to do anything other than very simple kinds of spin lock-like mechanisms. And we'll take a look at that. We'll talk about something called the simple blocking queue, which will be used to illustrate this point as we go through this set of slides. In particular, were we to try to just use synchronized methods to do stuff, we'd end up with busy waiting using spin locks when the data structures are at their boundary conditions. For example, in this case, if we have a queue, if the queue is empty, if you try to take from an empty queue, it'll basically end up spinning, or worse, it'll actually do worse things in this case. And if you add things, you could use it to spin. So bottom line is we don't want to use mutual exclusion alone for situations where we want stuff to sleep. And we talked about that a little bit when we talked about condition objects recently, and the same thing is true for built-in monitor objects and their coordination features. Because of the fact that mutual exclusion alone is insufficient, as we talked about when we introduced the concept of condition objects, built-in monitor objects also provide waiting and notification mechanisms. And it's done with this thing called the wait queue. And so the way you would typically do something like this is you would have a synchronized method or a synchronized block, and inside of that you can wait. And wait works very much like the await method does on a condition object, in the sense that it puts the calling thread to sleep and releases the so-called intrinsic lock. And that will continue until somebody notifies it that it can wake up and do its thing. So we'll talk about this stuff in more detail. We'll also talk about why you want to try to avoid using these features as much as possible unless your professor gives you an assignment where you have to use them. And then you have to use them after, in order to be able to implement the assignment. So the idea here is that if you try to add something to a queue that's full, then this call put will block as opposed to spin. And the same thing is true when you want to take something out of the queue. After you remove something, then you notify anybody who might be trying to put something in the queue that they may be able to make forward progress. And again, in this case, calls to take will block if the queue is empty. And that should sound very familiar. If we think about the discussions we had about array blocking queue earlier, same kind of idea. Java built-in monitor objects were put in there at the beginning of time, Java time that is, to help avoid concurrency hazards between producer and consumer threads. And basically what they're used to do is they're used to ensure that fields in objects or in classes, if they're static, have valid state even when that state is accessed concurrently by multiple threads. This is not any kind of a surprise, right? This is just the classic thing you've got with mutual exclusion. You want to make sure that if you have multiple threads, they're not modifying some shared mutable state in ways that will cause corruption. And in this context, valid state means that each method preserves key invariants when certain circumstances arise. So for example, here we have a priority queue that's sorted in ascending order, and we want to use the critical section to make sure that when we insert and remove elements in this priority queue, that the ability to maintain the sorted order is preserved whenever a lock is released. And so basically what that's saying is invariants need not be satisfied when access to an object is protected by a synchronizer. What that means is when this thread has got exclusive access to the critical section, meaning that no other threads can get in there and either try to read or write to this priority queue, then the invariant need not hold, because of course it's in the middle of changing things, right? If you're going to go in there and delete an element from the priority queue, then you want to make sure that nobody else can be accessing it simultaneously during that update. So it's okay to have the invariant not be satisfied as long as the lock is held. But when a lock is released, then the invariant has to be in place. So that's the end of a quick overview of Java synchronizers, in particular built-in monitor objects. And of course, we're going to go into this in way more detail in the rest of today. And that should give you enough to start working on assignment 2B, which will be out soon.